Inside this archive, information takes on vastly different physical shapes: glowing scrolls of text, dense crystalline structures, and hovering tables of light. At first glance, it seems impossible for a simple text note to share any common ground with a complex application or a sprawling database. But beneath the surface, these distinct forms disappear. Every computer file, regardless of purpose, is stored as a sequence of zeros and ones. Since a vacation photo and a grocery list are built from the exact same digital dust, the computer requires a method to distinguish the two. Correctly identifying these files depends on the specific translation rules applied to that underlying binary code. Text files such as .txt, .py, and .csv contain human-readable characters. These are the primary tools for storing simple notes and writing code. This diagram illustrates the process. Because a computer only stores numbers, it uses an encoding scheme like ASCII to translate them. When a text editor encounters the binary equivalent of the number 65, the encoding scheme tells it to display a capital A. To make text legible, the file relies on hidden formatting flags, like the end-of-line marker. In Python, this is typically the \n character. When the editor hits that marker, it breaks the current line, displaying the remaining content on a new one. By combining a character dictionary with these invisible formatting flags, text files convert raw binary into a document humans can easily read and edit. Binary files operate differently. These are used for images, audio, and complex data structures like dictionaries. They are stored as exact replicas of the data as it exists in the computer's memory. This diagram shows what happens if you open a binary file in a standard text editor. The software tries to apply ASCII rules to complex memory data, resulting in a series of nonsensical symbols and garbage values. The data is not damaged. It simply requires specific software, like a video player or an image viewer, to interpret the memory structure correctly. However, this direct storage method makes binary files fragile. Even changing a single bit within this data grid can have significant consequences. That single bit flip corrupts the internal structure, making the file unreadable to the application designed to open it. Binary files sacrifice the broad compatibility of text to achieve the storage efficiency required for machine-heavy operations. The CSV, or comma-separated values file, serves as a bridge between these two worlds, designed specifically for moving data between different systems. A CSV is a plain text file. It follows the same ASCII rules as a standard note, which allows it to be opened and read by any basic text editor. Here is a string of student data. The CSV takes the standard comma and uses it as a rigid structural divider rather than just punctuation. The computer uses these commas to break the linear string, snapping text into a grid of aligned columns and rows. This format provides the universal readability of a text file, alongside the organized structure needed for data analysis. We can now identify files by looking at their structural properties. Let's look at 3 streams of raw binary and determine their true forms. Stream 1 translates into a human-readable story that we can edit in any basic program. This is a text file. Stream 2 is a replica of a game's inventory held in memory. It requires specific software to avoid displaying garbage values, marking it as a binary file. Stream 3 uses ASCII characters, but employs commas to enforce a row and column layout. This is a CSV file. Every digital file starts as a sequence of zeros and ones. Text files prioritize human reading, binary files provide machine replicas, and CSVs organize structured data. Effective file handling in Python relies on knowing which set of rules to apply to the binary data you encounter.